Hey guys, welcome to my channel and welcome to this next video in the series on understanding the central limit theorem. So far we've talked about what the aim of this series is to go through each of the components of this theorem and understand it as if we have no mathematical background or very little mathematical background. So in essence, this is not a quick and a quick summary. It's more of an intense dissection. Maybe if you're like me, when you're a kid, you like to take apart something to see how it works. Well, I did that often. We had radios back then, and unfortunately, I could never put it back together correctly. But this one I can do. So let's go through here. We've already discussed, the breakdown of the theorem, and in the first video did sort of give the essence of what it means in some kind of way. Now, then we went through and we talked about sequences. We haven't talked much about random variables. That's basically our next step. So we're going to go through each of these topics: sequences of functions. We've done that in the first few videos. Random variables and independence. So we're actually going to be focusing on a part of the idea behind random variables today. And today we're going to be focused on something called a sample space. So yeah, we talked about sequences. We talked about convergence and divergence of sequences. And these are just sequences of numbers, integers or natural numbers. And then we talked about sequences of functions, which prepared us to be able to discuss sequences of random variables, because it turns out that a random variable is a function. Okay, and so that's our focus today, is to break down this idea. Let me go back to the statement of the theorem. It says that we've got a sequence. Okay. So that we talked about sequences of independent and identically distributed random variables. Okay, so and they're converging in distribution, which is a special type of convergence. So today we need to talk about what are random variables. We know they're a type of a function, and we know they're going to be converging. So that's the reason why we talked about convergence and functions. And we'll talk about independent and identically distributed. But first, back to random variables. And so let me go way back over here. I went too far. Here we go. So we're going to be talking about random variables. And in particular, the first thing I want to talk about is their domain. So according to our definition, you see here, a random variable is a function x from omega. This is our omega to r, which is the set of all real numbers, that assigns a real number to each outcome in the sample space omega of a random experiment. Okay, so today we're going to talk about this thing called a sample space omega. And you might also see it called S. And so let's get started with that. And what I want to do is I'm going to write all this down on my little notepad here. So let's clear this. And let me change some screens here. There we go. And change around one other thing. This is it. Okay. There we go. I wonder how people would think about this if they traveled in time and saw people doing classes like this. Okay, so today's focus, I'm just going to define what is a sample space, basically. So we've got definition. So a sample space, and hopefully you can read my handwriting. A sample space omega is you can think of it as a set or a list. We'll call it a set, is the set of all possible outcomes of a random experiment. Okay, so a random experiment, we talked about this before. It's where we do something that's repeatable, like flipping a coin, and the outcome of that action is determined by chance, right? So this is the idea of a random experiment. Now, there's many other examples of random experiments, thankfully, like selecting 100 people from a group of 100,000 or 100 million or 1 million, right? Selecting 100 people from a group of 1 million randomly. You could do it any number of ways. You could throw something out and see where it lands, or you could assign the 1 million people a number and then use a pseudo random number generator to select them. So many ways to do this. All right. But the sample space includes all of the possible outcomes. And before I get into the axioms of what makes a sample space, let me just provide a little note here. So the note is that, hold on a second, something wrong with my pen here today. So the note is that omega must be the following. So it must be one, collectively exhaustive. So what does that mean? It means that it includes every possible outcome. Okay. 2, all of the outcomes, which we'll come to call events. So let me just go ahead and get that established now, because I'm going to be using the word event without thinking about it, that you haven't learned it yet. So the outcomes are, we're going to call the outcomes events. Okay. So if I flip the coin and it lands on tails, that outcome is the event that the coin lands on tails. Okay. So that's how we will describe outcomes. We'll describe them as events. It must be that all of the events are mutually exclusive. So again, if I flip a coin, it can land on heads or it can land on tails, but it can never do both. So at the end of the experiment, there is only one outcome that is possible to have happened out of all of the possible outcomes. All right, and then the sample space, it must not include any, it must only have the necessary information and nothing less or nothing more. So we'll say must only include necessary info. We'll say it like that. So it can't have anything less, it can't have anything more. Okay, so then let's talk about the axioms, okay, and this word event. So in a sample space, so let's say I've got my experiment here. I'll just give you the easiest example possible. The experiment is the coin toss. This is the classical example. And if you've studied probability, you're probably rolling your eyes at seeing this example again. I know I have. So yeah, but it's just like the most simple, suitable type of example. Where are the rectangles at? Okay, I can't find the rectangles. Okay, so here's my sample space. And I'm going to call it omega. So in the example of tossing a coin, right? Our sample space will include basically 2 outcomes. We have heads and we have tails. And we only have heads and tails. We have nothing else. Let me give you another definition. And these are mutually exclusive, so I could just like draw a little line down the middle of this. Okay, so that's a visual representation. So now let's go with another definition. We'll say that an event is a subspace, not subspace, sorry. It's not a space. It's a subset of a sample space. So in this case of the heads and tails, we'd say that event where it lands on H is a subset. So you can see, I've broken the little sample space into two pieces. And we talk about, so what does the sample space do? What is our definition? We said that it's a set of all possible outcomes of a random experiment. And then what does a random variable do? A random variable, which we'll talk about in more detail later, assigns a real number to the outcome in each sample space. So in other words, what a random variable does is it gives us the probability of an event. And the way we talk about probability of an event is we say something like this, P of H. Okay, so here I've got P of H is the probability that the coin will land on heads. So that is the event. Land on heads. And this is how we describe probabilities, right? We say P of event. P of event means that there's some numerical value between, and we'll talk about how it's bounded in just a moment. There's some numerical value that we can assign to the probability of some outcome from a sample space occurring. Okay, so the event is the subset of a sample space, and we assign, so here's the note here, we assign probabilities to events. So, and of course, a probability is a real number, and it has lower and upper bound in this case of our sample space. So let's talk about the axioms of a sample space. So the axioms of a sample space, they give us the structure that governs what a probability can be and how they're actually related. So the first axiom is that so given a sample space omega with events, we'll say A, B, and C, we have that number one, probability of any event must be greater than or equal to 0. So we have no situation where our probabilities can be negative. Okay. And then the second thing is that we have that the probability of omega, which is to say that you can think of it like the probability that the outcome that occurs will be in the sample space is 1. So like it must be the case that the only possible outcomes are in the sample space and there are no other outcomes than those, so that we could say the probability of omega is equal to 1. And then if we have 3, so 3, if the intersection of two events is empty, okay, then we have what's called the additivity rule, probability of A, probability of A or B is equal to the sum of their probabilities. And actually, it turns out that we could also just say this as an addendum. If this is not empty, then we just subtract that part off. The probability of A or B is equal to the probability of A plus the probability of B minus the intersection, because we don't want to count that twice since we're counting A, probability of A, probability of B. Okay, so what have we established here with these axioms? We've established the possible values of the events, of the probability of the events in the sample space. Okay, now how exactly have we done that? Let's think about a sample space that has only two outcomes. And our outcome will be, our event will be the event A, and then we'll have over here the event that's not A. Okay, so clearly if this is omega, then we can see that if I take the union of A and not A, I will get the entire sample space. Okay, so it means that if I look at our axioms here, the probability of omega must be equal to 1 here. Okay, and so that means that this probability is also equal to 1, but by definition, by definition, we have that the intersection of A and not A is necessarily empty or disjoint, if you like. So that means that that 1 is equal to the probability of A plus the probability of not A. And that means that if we want to know the probability of A or the probability of not A, I can simply rearrange this. If I have one or the other, I can say that the probability of A is equal to 1 minus the probability of not A. And definitely this will be less than or equal to 1, right? Because the entire probability of the sum of them is 1, right? And so also we get that, let's see, how can I say? Okay, so also we get that we can do it the other direction as well. 1 minus P of A. Okay. All right, so then we can also get this idea that the probability of omega, so this is equal to 1, right? We definitely know that this is equal to 1. But also, let's say I want to talk about not omega. So how can I quantify the probability of not omega? And we can do like this, omega, not plus, sorry. So think about it like this, omega in union with, no, not in union, sorry. sorry. So omega intersected with the complement of omega, again, by definition, like a set and its complement are disjoint. So that means that we can apply the additivity axiom here, right? This one. So that's going to apply here, so that we can say that the probability of omega plus the probability of not omega. Well, we already know that this one is 1. plus, so it's going to be 1 plus the probability of, oops, I put the complement in the wrong spot. We already know that this is equal to 1, so it's going to be 1 plus the complement of the probability of the complement of omega. So let me write it down here. So basically, what have I got? I know that it's 1 plus the probability of the complement of omega, but this is equal to, so these are equal, right? So how is this supposed to be working? Well, it works like this. So 1 plus the 1 is equal to probability of omega plus the probability of the complement of omega. So it means that since this is equal to 1, then it must be the case that this one is equal to 0. Okay, so one more thing here. So let's see if I made any sense just now. So we know that the probability of omega is 1, and also that the union of these, so if I add them together, it has to be equal to 1, because that's basically like the maximum number that it can be, right? And because that's the maximum number that it can be, and we know that this one's already 1, this one has to be 0. And one more thing here is that what is this thing? What is this complement of omega? Well, we said that omega is the sample space and that it includes every possible outcome, and it must include every possible outcome so that anything that's not in omega is not a possible outcome. So in other words, that this is the empty set, or the null set, if you like. So what we've established here is that, in a roundabout way, is that the probability of the empty set is 0. So there must be, in other words, there must be an outcome that occurs that's in the sample space, in other words. So it's impossible to do the random experiment and not have an outcome that's in the random experiment. Okay, so I think that's what I'm going to stop with today. Actually, is that what I want to stop with? Yeah. So let's just recap summary. And then the next video, I'll explain about the 2 different types of sample spaces we're interested in. So here's a summary. So omega is defined as a sample space. Okay, and we can use some people use S, right? Sample space. A sample space is the set of all possible, and we could put in brackets here, mutually exclusive outcomes of a random experiment. And we know what a random experiment is. Okay, so let's make some bullet points here. Oh, wait, that's not the right place for that one. Oh, no. Hold on. Random. Okay. Bullet point 1, bullet point 2. And an event is a subset of omega to which we which we assign a probability, and that probability is a real number value, right? And we talked about that for these probabilities of events. So if omega is a sample space, we talked about that these real number values, the outcomes are, the probability of the outcomes are bounded. If omega is a sample space with event A, then what did we figure out here? Then the probability of A is greater than or equal to 0. It's also, what do we show? The probability of omega is equal to 1, which implied that actually this P of A is bounded between 0 and 1. And also we showed the probability of the empty space was 0. So this is axiom 1, axiom 2, axiom 3. And then we've got additivity, which is that, let's see, with events, let me add another event, A and B, which is that if the intersection of A and B is empty, then we can find the probability of both of them happening or one of them happening. So the probability of the union is equal to the individual probabilities added. Okay, and that's it for now. So in the next video, so I'm really going to dive into this part, and we'll emerge back again once we've discussed exactly how we can assign probabilities to events in a sample space, because I think this is really, first of all, it's really interesting, but also it's important to understand how we are equivocating, at least it's in some naive level, how we're equivocating, not equivocating, I just keep saying that word wrongly, how we are using areas under a curve of some distribution or some probability density function to calculate probabilities, to quantify probabilities, right? And so we're going to dive into this sample space details until when we go back and we look at, even if you were to look at a t distribution, or in this case a z distribution, we can understand how this probability is assigned and calculated to this event that's in this sample space. Okay, so I think this is going to be really interesting for you. Definitely for me. So in the next video, we're going to talk about two types of sample spaces. We'll talk about, number one, discrete. So for when we have discrete variables, and then number two, we'll talk about continuous. Okay, so these will be corresponding to the probability mass function and the probability density function. So how do we assign probabilities to these different types of data? Okay, that's it. Hopefully this is helpful. If you have any questions, comments, concerns, if you noticed any mistakes, or if you find that you have an insight that I could benefit from, please list it in the comments below. Thanks so much for watching, and take care.